In this lecture, we will begin with the application of Laplace transforms to solve linear ordinary differential equations with polynomial coefficients. So until now we have seen how to solve the linear ordinary differential equations with constant coefficients, whether it is an initial value problem or a boundary value problem. We have solved both kinds of equations, and now we will look at linear ODEs with polynomial coefficients. So, and as an example, we have taken here this differential equation t y double prime plus 2y prime plus ty equal to 0 with only one condition, y 0 plus equal to 1. So, this is the limit as y t goes to 0 from the right hand side. This is given as 1. So, for these kinds of equation, we use the property of the Laplace transform, which is multiplication by t. So, we remember that the Laplace transform of t to the power n ft is equal to minus 1 to the power n, the nth derivative of the Laplace transform of ft at s. So, we will use this property to solve these kinds of linear ordinary differential equations with polynomial coefficients. So, let us apply this here. So, we will have the transformed equation taking Laplace transforms on both sides of the differential equation. So, the first one is the Laplace transform of t y double prime. This is equal to minus d by ds of the Laplace transform of the double derivative, which means this is s square ys minus s y 0 plus minus y prime 0 plus. So, since this is a constant, so assuming that this is a constant, and we will assume throughout that yt is piecewise continuous and y prime t is also piecewise continuous and of exponential order. So, all our properties for the Laplace transforms are applicable. So, in this case, the Laplace transform of t y double prime, this is the derivative of this expression. So, this is d over ds of s square ys plus d over ds of s, simply because y 0 prime, this is y at 0 plus is 1. So, this term is 1, and this term, this is minus 2s ys minus s square y prime s. So, we will have minus 2s ys minus s square y prime s plus 1 plus 2. So, this is the Laplace transform of y prime. This is sys minus 1. This is y 0 plus. And then we have Laplace transform of ty, which is again the minus 1 times the derivative of ys. So, this is again y prime s. So, we can rewrite this as s square plus 1 y prime s equals, so minus 2s ys plus 2s ys will cancel out, and you will have minus 2 plus 1, this is minus 1. So, therefore, y prime s is minus 1 over s square plus 1, and so this is again a differential equation, and you can integrate on both sides, to get ys as minus of tan inverse S plus the constant of integration C. So now we cannot use any other initial conditions because only one initial condition was given, and this was for y and not capital Ys. So we still have to find out what is this constant of integration C. So then we apply our knowledge of the behavior of the Laplace transform. So we know that the limit S goes to infinity of Ys, this is 0. This was the one of the properties of the Laplace transform. So this implies if you take the limit on both sides, you get a 0 on the left side and you get minus pi by 2 plus C on the right side. So this implies that C equals pi by 2, and so Ys is pi by 2 minus tan inverse S, which is equal to tan inverse 1 over S. So now we know what is the inverse Laplace transform of such a function. This is simply sine t. So this is our yt, is sine t over t. So we have seen that transformed equation can be itself a differential equation in Ys. So this is a differential equation in Ys, and we have to solve another differential equation which might be simpler, which may not be simpler than the original equation. So this kind of method may not work for all cases when you have to transform an ordinary differential equation which has polynomial coefficients to the Laplace domain with S variables. Then you will get another differential equation which may or may not be easier to solve than the original one. So it's not always applicable. Another example where the Laplace transform Laplace transform technique fails. This is given by the following differential equation: y prime minus 2ty equals 0 with the condition y0 equal to 1, y prime 0 equals 0. So, well, y prime 0 is not needed because we have only the first order differential equation. Now the solution to this differential equation is e to the power t square. As we can see, y prime t equals 2t e to the power t square, which is 2ty t. So yt is a solution to this differential equation, but the Laplace transform of yt, as we know, does not exist. So one has to be careful when we apply this kind of when we apply our Laplace transform technique to this kind of equations. It may not always work. Let's look at a special equation, special kind of ODEs with polynomial coefficients. So the first equation that we will look at is called Bessel's equation, and this is for any n, a positive integer. You have this equation t square y double prime plus ty prime plus t square minus a square n square y equals 0. The solution to these differential equations are called Bessel functions. For n equal to 0, the initial conditions are y0 equal to 1 and y prime 0 equal to 0, and the solution, so let me call this differential equation star. The solution to star is called the Bessel function of order 0. So this is for n equal to 0, and denoted by J0 of t. So let's try to find what is J0t from our differential equation with the initial conditions y0 equal to 1 and y prime 0 equals 0. So our differential equation is t square y double prime plus ty prime plus t square y equals 0. So you can get rid of one of the powers on each term. So it's simply ty double prime plus y prime plus ty equals 0. So let's take the transformed equation. So the first term gives s square ys, so minus d over ds of s square ys minus s times 1 minus 0. This is y0 and this is y prime 0 plus sys minus 1 plus minus d by ds of ys. This is 0. So we will get, for the first one, 2sys plus s square y prime s minus 1. The second term is sys minus 1 and the third term is y prime s again. So now we can collect terms for y prime s. So we get s square plus 1 minus y prime s, and this is equal to sys, and then the constant term, this is plus 1, this is minus 1, they cancel out. So this is our equation for the transformed equation. So we get the differential equation y prime s over ys equals minus s over s square plus 1. So one can integrate on both sides to get log of ys on the left side, and you will get on the right side minus half log of s square plus 1 plus a constant of integration c. So this implies that ys, so if you take the exponential on both sides, you will get ys equals c over square root of s square plus 1. So now we have to determine c. So if we take the limit as s tends to infinity on both sides, gives 0 equals 0, so you don't get anything, but we can still apply the initial value theorem. So we know that y0, which is limit of t tends to 0 plus y0 yt, this is given as 1, and so we know that the limit t tends to 0 plus yt is equal to the limit s tends to infinity sys, and this is the limit as s tends to infinity cs over square root of s square plus 1. So this limit c times limit s tends to infinity s over square root s square plus 1, this is simply, limit is 1, so you only get c, and on the left hand side you get 1. So this means that c equals 1, and so ys is simply 1 over square root of s square plus 1. So now the question comes how to invert this kind of function. question is how to find L inverse of 1 over square root of s square plus 1. So one way which we didn't cover before is via infinite series. So by the binomial theorem, by the generalized binomial theorem, you can write 1 over 1 plus s square to the power half. This is 1 plus s square to the power minus half. So let's rewrite this as 1 over s times 1 plus 1 over s square to the power minus half. So this will help us have the power series in 1 over s square, so that inverting it will give us something, some powers of t. So what we get here is the following series. It's the first term is 1, then you have minus half times 1 over s square, then you have plus half times 3 over 4 times 1 over s to the power 4, then again minus half 3 by 4 5 by 6 times 1 over s to the power 6, and so on. So this is an infinite series, and this can be rewritten as 1 over s minus half times 4 factorial over s cube, and finally we get this series 1 over s minus half 2 factorial over s cube plus 1 over 2 square times 4 square, 4 factorial over s to the power 5, and so on. And now these terms are precisely the Laplace transform of t square, Laplace transform of t to the power 4, and so on. So we will like to invert it term by term. So in L inverse of 1 over 1 plus s square square root is equal to L inverse 1 over s minus half L inverse 2 factorial by s cube plus 1 by 2 square times 4 square, L inverse 4 factorial by s5, and so on. And this, each of these terms, this is 1, and then you get t square, then you get 2 square times 4 square t to the power 4, and so on. And this is an infinite series for J0 t. So we can use this infinite series method. So let me state it as a remark. We can use term by term inversion of Laplace transform in an infinite series given by, say, n equal to 0 to infinity an times 1 over s times n plus alpha, where alpha is greater than or equal to minus 1. So we can have fractional powers of alpha as well. So this can take care of n plus alpha takes care of fractional powers. So we can use term by term inversion of this kind of this kinds of infinite series if the modulus of an is less than or equal to k times alpha, well, not alpha, some constant c to the power n over n factorial for all n greater than or equal to 1, for some constants k and c positive. So if this condition is satisfied, then one can use term by term inversion, and you can get immediately the inverse Laplace transform of these 1 over s to the power n plus alpha, and the answer is simply that powers of t that will come here instead of 1 over s to the power n plus alpha. So you will get an infinite series answer for an infinite series inversion. So this was our Bessel function for order 0. Now we come to Lagruerre's equation. This is given for any positive integer n greater than or equal to 1 by the differential equation ty double prime plus 1 minus ty prime plus ny equals 0. So let's look at the transformed equation taking Laplace transforms. So the first term is again minus d over ds s square ys minus s y0 minus y prime 0. Then the second term has two terms. First is y prime. So for y prime you get sys minus y0, and the other is ty minus ty prime. So for that you get plus d over ds of sys minus y0, and the last term is simply n times ys. This is equal to 0. So let's see what we get. So for the first one you get 2sys plus s square y prime s minus y0. This is the first term. Then you get sys minus y0. This is the second term. The third term is sy prime s plus ys, and the last term is simply n times ys. This is equal to 0. Now notice that y prime 0 vanishes from this equation because it's under the derivative and it's a constant. Now y0 will also cancel out. So this y0 and this y0 cancels out. So in the end you will get minus 2sys minus s square y prime s plus sys plus s times y prime s plus n plus 1 times ys. This is equal to 0. So now let's try to find the differential equation by taking all the y prime together. So you get, so there is one term here and one term here. So you get s square minus s times y prime s with a minus sign. This is equal to ys plus n plus 1 times ys. This is equal to 0. This implies that s square minus s y prime s is equal to n plus 1 minus s of ys, and so the differential equation is y prime s over ys is equal to n plus 1 minus s over s square minus s. So now we can try to solve this equation explicitly over ys. So we will expand it in partial fractions. So this is n, note that this is n plus 1 minus s over s times s minus 1. So you can write this as a partial fraction, a1 over s plus a2 over s minus 1. So one can easily find that a1 plus a2 equals minus 1 and minus a1 equals n plus 1. So this implies that a1 is minus n plus 1 and a2 is equal to minus 1 plus n plus 1, n plus 1, this is equal to n. So therefore we get minus n plus 1 over s and then plus n over s minus 1. So we can solve this equation. We get ln ys equals minus n plus 1 ln s plus n ln s minus 1 plus some constant of integration c, and we can take them together to get ys equals some constant c, and you will get s minus 1 to the power n over s to the power n plus 1. Now again, we know we have already computed the Laplace transform of Lagruerre polynomials, which gave us this answer s minus 1 to the power n over s to the power n minus 1. So remember that the Lagruerre polynomial of for n is given by the formula e to the power t over n factorial, the nth derivative dtn of e to the power minus t to the power n. So this was our Lagruerre polynomial, nth Lagruerre polynomial, nth. So we can easily compute that the Lagruerre polynomial at t equal to 0, this is simply 1, and so this implies that c equal to 1 as well, and so yt is ln t. This means that the solution yt is a constant multiple of ln t, and so this is for some constant c, which can be determined for a given initial condition, can be determined for given initial condition. So for example, if we put y0 equal to 1, then c is equal to 1, because ln 0 is also 1.